Less and less as you know about it. Thank you. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Welcome to EE123, Lecture 5. Woo! Wonder what the frequency is. Today, my favorite lecture. First of all, thank you very much for coming. It's a rainy day, rare in California, so people just don't understand what's going on. What is this moisture coming on my face? Not clear, right? It's also a Friday. Happy Friday. Happy Friday. Yay. It's a great week. Okay, so before we start, and then you're going to Before we start, I just want to talk about an interesting project. It's called Pocket FM. There's a short story. I'll put a small piece of the NPR story right now, so just listen.
Syria is one of the most dangerous countries in the world for journalists, according to Reporters Without Borders. Still, independently produced, local, and other news important to Syrians is starting to thrive, thanks to a team of Germans and Syrians running a pirate radio network from the heart of Europe. As Mina explains, that's the story.
This is Syria Radio Network, or SERNET for short. It broadcasts news and shows from 9 Syrian pirate radio stations, most with studios in neighbouring Turkey. They all have reporters on the ground, but because of the bloody civil war in Syria, they have problems getting their dispatches to the Syrian people. Najat Abdulhak is from the German NGO Media and Cooperation and Transition.
They have a day-to-day local services, like which borders are open, what is the exchange rate of the Syrian lira, what is the price of diesel, or if the schools are open.
While the network is opposed to the regime of President Bashar al-Assad and so-called Islamic State, or ISIS, Abdulhak says SERNET strives to produce accurate and balanced reporting. The Berlin NGO says it only works with members of moderate opposition groups.
There's always debate about what is news, what is propaganda, and we really work on them to avoid to have any broadcasts to encourage violence or to encourage any bloody actions.
But without this German NGO, SERNET's reporting wouldn't reach Syria at all. Frequent electricity cuts and erratic internet connections make online broadcasting difficult. So the group's engineers in Berlin have resorted to using old-school analog technology.
Satellite and
Okay, so from a technology point of view, this is very interesting, as well as from a human point of view. But these guys created this device, which is an FM radio that broadcasts on the FM broadcast frequencies. But what it does, it has the ability to capture satellite, satellite data, and then transmit it, retransmit this locally. You can either use some other audio source or computer source or anything, and basically it makes it into a small FM radio station. But it has this really nice integration that they put into it, where you can use solar or some battery supply to operate it. It has about 6 kilometer radius in range, and the nice thing about it is that people in general will have an FM radio to listen to. So if you want to create something either in war-torn areas or disaster areas, and to be able to communicate, you can have one of these devices just put there and be able to get information out. So it's a really nice integration of a lot of interesting things into a small piece, and this comes because you have now the ability to make electronics more inexpensively. So I think this is I thought it was a nice project to see. And if you think about from your point of view, I mean, with the software-defined radio that you'll be getting, you could probably decode satellite information pretty easily. Then have a Raspberry Pi that interprets it, and then all you need to do is have an FM transmitter that would retransmit whatever you're sending. So you could probably make such a device. Okay. Information. Last time we finished DTFT chapter 2, spent 12 minutes on the Z-transform chapter 3. Today we're going to talk about DFT. Reminders.
Okay, so other than the reminders that homework 1 is due tonight, homework 2 will be out today. And a little bit about the lab checkoff. So we did some of them yesterday. But in general, the lab checkoffs will be the following week. So after the lab is due. So the lab is due yesterday at midnight, but the checkoffs are going on next week. And what we'll do is we'll ask you to download the notebook that you uploaded to B Courses and just answer some questions and demonstrate that you did the lab. And then also in the future, the labs can be done in partners, and we'll talk more about that on Tuesday. And finally, I'm out of town on Monday, so Frank will be giving the discussion. Oh, and I should mention that some people didn't know that there's a Piazza page. So make sure you know that there's both B Courses and Piazza. All announcements are on Piazza. We only use B Courses for things we don't want to share publicly with the rest of the world. So that's it. Any questions?
So quiet.
They get it.
They get it. Yeah, absolutely. Or you can just, if you don't want to share, you can just transmit it on FM. Okay. Any questions about last time, quickly? On homework, by the way, you have this beautiful question about the, what's the name of the filter? The Savitsky-Golay filter. I think it's a really nice one. It's quite surprising that if you do polynomial fit, local polynomial fits, comes down to be something interesting and actually quite simple. And people made a big deal out of this, like it's considered one of the most seminal papers in analytic chemistry. So if you just think about very closely what it actually means. So that's the question about. And if you're interested, just go also read the paper. Okay. The DFT, the discrete Fourier transform. Now, the cool thing about this, first of all, that we talk about this class is because it's discrete and it's the Fourier transform. Fourier transform is an amazing thing, lets you analyze signals and look at their frequency content, and now you can do it in discrete time. Okay? So the motivation for it is really that if we are going to do some spectral analysis or analysis of the frequencies, we need to be able to sample that, right? So any numerical analysis needs to be able to have discrete representation, both in samples as well as discrete, like in floating point, right? Floating point or doubles and so on and so forth. Okay. But the thing is, if you sample in one domain, you get periodicity in the other domain. We saw that for the DTFT, right? We sample in time, or we just get discrete samples. Then we get the DTFT, which is periodic in the frequency domain. So now what happens if we sample in the other domain, in the Fourier domain, then we're going to get also periodicity in time. Okay? So so one candidate that you can think of is the discrete Fourier series that you covered in 120, and those of you who've taken 20. Who has not taken 20? Are you like the 16 thing? Or no? Or just like skipped it? Okay. Yes. Yeah, okay. All right. Next year we're going to start getting the 16s. We'll see what happens. Okay, so what about the discrete Fourier series? Well, it is periodic in time, but it's also periodic in frequency, right? So that's a good representation. Okay. But the real question is, what if you have signals that are non-periodic? Okay. What if I have signal that something is not periodic, I want to perform analysis on it? Well, in that case, we're going to still use the DFS, or discrete Fourier series, interchange it with a t instead of an s. It's going to discrete Fourier transform. But we'll have to have special considerations there. And you see, it's going to be very similar. But again, like a lot of things, it's same, but different. Okay? So conceptually, it will be different. And we're going to talk about that. So the cool thing about the discrete Fourier transform is that when you want to compute this, there's an efficient way to do this. If you just think of a trivial way of computing a discrete Fourier series or a discrete Fourier transform, it is an order of n squared with the number of measurements that you have. And that's expensive. N squared is expensive. But there exists what's called the fast Fourier transform, okay? FFT, which can compute all this, the exact same thing with just n log n type of operations, okay? Which is huge. Okay, huge reduction in computation. Actually, it made everything possible in terms of, like, it just changed the way, signal processing is done. Once people have figured out you can compute discrete Fourier transform fast. Okay. Now, there's this efficient library that already exists, like the FFTW, the fast Fourier transform, fastest Fourier transform in the West. Okay. In Python, if you want to use that library, you just called np.fft of x. Okay. And if you want to compute the inverse one, then just replace that with an IFFT. The other cool thing, if you want to compute convolutions, why would you ever want to compute convolutions? Why? Filters, systems, right? All this stuff. So if you think of a discrete convolution with a large filter, again, computation is squared with that filter size. And then using FFT-based convolutions, you can go, again, back to n log n, which is huge. All right, so let's do a short review of what is the discrete Fourier series. The definition is that you're going to consider periodic signals. So tilde here is going to relate to a periodic signal. Okay, so x of n has a period of length n, and so by definition, x tilde of n plus capital N will be equal to x of n. That's just from periodicity. And in the frequency domain, it's also going to be periodic, and it's again in the same way. Okay, so tilde means periodic signals, periodic spectrum. And then we're going to define the following W sub capital N, which is going to be e to the minus j 2 pi over n. This beautiful, beautiful thing. Okay, I have to say e to the j. I mean, what a great invention. Like, you take something that is real, you take it to the power of something that's imaginary, right? I'll show. Okay, I'll get there's a nice cartoon by XKCD about that, but I'll show you next time. If I don't, remind me. Okay, so by definition, if we want to compute the discrete Fourier series, we sum over from n equals 0 to n minus 1 basically over a period, and using this kernel, which is w sub n to the power of kn. Okay, and we sum over, in that case, over n, and we get the k's. If we want to do the opposite, and we put a minus over here, and divide by 1 over n. Remember this? Who has not seen Fourier series before? Okay, moving on. What are the properties of this w sub n to the power of kn? It has really beautiful properties. It's like clockwork, if you think about this. So it is periodic with a period of capital N. So w sub n to the power of 0 is the same as w sub n to the power of n and 2n and so on and so forth. They all equal to 1. Okay? They all equal 1. So, like, think about it. You take a non-rational number, you take it to the power of a imaginary number, and you get 1. Crazy, right? Something non-rational, take the power of something imaginary, and you get 1. Right? You're not impressed, but, like, think about it. Whew. All right. The other thing is if you take to the power of k plus r, it's the same as multiplying them. It's also the same of summing them. And then because, okay, it's the same as multiplying them. If you add a capital N to this, it doesn't change because it's periodic. And here's just an example for n equals 6 for n equals 6. So if k equal 1, if you start varying n, then it's like, going on a circle. N equals 0, n equal 1, n equal 2. That would be basically what the vector is. It's a unit vector with a certain phase. And it's going to be like clockwards, and it has a period of 6. Okay? For k equal 2, if you then start varying n, now it starts going faster. Okay? So it's like faster frequencies. So you jump more and more, but then again, it's still periodic. Okay? So this is how it behaves. All right. So that's DFS. What is the DFT? Well, by convention, because we want to deal with non-periodic signals, okay, we're going to assume that we're going to be working with just one period, okay, by convention. So if you have something that's non-periodic, you can call it periodic, but just look at this one period of it, okay? And we're going to assume that otherwise the rest is 0. So it's going to be equivalent to this over the tilde one, the periodic one, over one period, but we're going to assume otherwise it's 0 everywhere else, by convention. And the same thing in the frequency domain, we're going to assume, hey, watch out. We're going to assume that it's going to have values of that periodic signal over one period, but the rest is 0. Well, Mickey, come on. What are you telling us? This is exactly the same. Well, it's kind of the same, but it kind of isn't from a conceptual point of view. Okay? You'll see what I mean, or maybe you won't, but I'm going to try at least to explain what it means. So here's the thing. This is the discrete Fourier transform. Wait a second, Mickey. This is exactly like the DFS. But wait a second, class. It isn't. It doesn't have a tilde. Okay? That's the difference. Because x of n is actually non-periodic, right? It is a signal. Okay? It is a signal that we're going to assume that it's finite. Okay? It is a finite signal. It is not periodic. Okay? And that's the difference. Okay? Because for the DFS, we're assuming kind of like infinite long sequences that are periodic. For the DFT, we're considering signals that are just finite. Okay? The equation turns out to be the same. But we're not talking about periodic signals. Okay? The analysis could be the same if you make them periodic. But that's the only difference. It's just conceptual. Okay? So we understand when you compute this, that x of n is 0 outside of the period from 0 to n minus 1. Okay? And we're going to assume that x of k is also 0 outside of that period. Okay, so you can write it that way. So it's x of k equals to the sum of x of n omega, right? So you've seen this before. That's the analysis part, and the inverse DFT will be the synthesis. Okay, think about that. Okay? We analyze frequencies, and then once we have frequencies, we can synthesize back the signal. As it turns out, this is an orthogonal transformation. Okay? It preserves length. It preserves energy by the Parseval theorem that you're going to see a little bit later. And it preserves the size. Now, there's an alternative way that you can write it. And one way, for example, is an orthonormal. So not just orthogonal, but also orthonormal. So if I instead, let me skip between these two. You see here, to go forward, there's no scalar. To go backwards, you divide by 1 over n. You can also write it that way, where to go forward, you divide by square root of n. To go backwards, then you divide by square root of n. And so this is an orthonormal representation. Why use one or the other? Well, sometimes this is nicer. And it's nicer because for orthonormal transformation, the adjoint or a transpose conjugate of a matrix, if we represent it using a matrix, is the same as the inverse. That is not true transpose for the orthogonal case. There's going to be a scalar there. So some iterative algorithms that you might want to use, maybe orthonormal representation might be simpler to implement. The reason that people have chosen to do this is because often you would compute the forward. You use the DFT for analysis. When you use it for analysis, multiplying by something is just waste of cycles. So that's why. Okay. That's the only reason. And here, you have to multiply on both directions. So it's just wasting cycles. The other way, you don't. But that's pretty much it. So here's a comparison between the two. Okay. In a DFS, we assume a signal is periodic with a period of n. So my signal, x tilde of n, is going to look like this. For the DFT, we're going to deal with finite sequences. Hence, my signal is just going to be that. The rest are 0. That's our assumption. And when you compute the DFS, we're going to assume that the frequency is also periodic. And here, we're just going to assume that it's going to be between those values and 0 elsewhere. Okay? All right? Conceptually. Similar mathematics, but conceptually, that's the difference. Yes?
So, quick question. Do you have, let's say you have endpoints.
Yep.
Your DFT is also going to be an endpoint DFT. But let's say your...
Who said that your DFT is going to be an endpoint DFT?
No, I'm just saying, is it okay to make it, increase the resolution and frequency, but you actually gain more information from that? Or you're just replicating it?
So the question is, if we do a more than an endpoint DFT, do we get more resolution or more information? Hold that thought. We're going to get there in a second. Maybe 2 or 3 slides. Okay? So that was a good question in the sense do we have to take an endpoint DFT? Well, in this case, you have a period of n. Yeah, so DFS is going to be over an n. But here, we have a finite sequence. Maybe my signal actually has zeros in it that I want to put in the analysis. Okay, what does it actually even mean? Okay, right? I can actually decide I'm going to compute a 20 endpoint DFT. What does that even mean if I have zeros in my signal? We're going to get to that in a second. So here's the example, okay? Let's say I have the following sequence. It's a discrete rect from 0 to 4, okay? And I'm going to compute a 5-point DFT. When you compute a DFT, you have to decide at what length you're going to compute it. Okay? Okay. So x of k equals to the sum of n equals 0 to 4 of 1 times omega sub 5, w sub 5 to the power of nk. And it's only true for k equals 0, 1, 2, 3, 4. Otherwise, the result is going to be 0. Okay? That's by definition what the DFT is. Okay? If you think about what it actually is, well, you just sum ones, right? So this will be actually only 1 for k equals 0, and it will be canceled for anything else. Okay? If you compute what it actually is, right? So then in that case, you got 5 times delta k. So it kind of makes sense because if we just look at this is a constant signal. The Fourier transform of a constant signal should be an impulse. Right? Pretty much. Does this make sense? What if you put any other k here? Like k equal 1. Okay? So if you sum over that, you get the whole circle. Okay? You always get something like symmetric, and they're just going to cancel. All the phases are just going to cancel each other. Okay? If you sum them. I'm seeing puzzled eyes, but we'll get to that. But I can also compute a 10-point DFT. What does it mean, a 10-point DFT? Well, I'm just going to sum from n equals 0 to n minus 1. And I'm going to use now w sub 10 instead of w sub 5. What it really means is that now my x of n is, goes all the way. And I'm going to actually include those values in the calculation. I'm going to assume that this is part of my signal. And I know that my signal is really 0 over here and also 0 anywhere else. This is also equivalent, okay? This is also equivalent to the case where x of k equals to x tilde of k, where small x tilde has a period of 10. So now, instead of having a constant x tilde, now my x tilde is going to look something like that. That's periodic. That's the equivalent. Okay? So this is why conceptually it is different. Okay? The 10-point DFT of x of n is equivalent to a discrete Fourier series if x tilde of n has a period like that. That's the equivalence. So now it changes, right? So now it changes. And so if I do that, I'm going to get a sum, still from n equals 0 to 4 because the rest are 0, but now over w sub 10 to the power of nk. Okay, so now it changes because I added those zeros. So this is a 10-point DFT. And if you want to compute now what is this 10-point DFT, you can show that you just put the sum in. It's going to correspond, like if you just sum over this, okay, it's a finite geometric series. It has an equation. It's going to come down to be sine pi over 2k divided by sine pi over 10k. Okay, you just evaluate this, do the math. It looks like this. This is a 10-point DFT. So now it's different, right? I computed a 5-point DFT over sequence. I get an impulse, right? Now I compute a 10-point DFT. It doesn't look like an impulse anymore. Strange, right? Right? The reason is not really strange because there is something interesting corresponding to what is the DTFT of that finite sequence and the DFT of that finite sequence with different lengths of DFT. There is a correspondence. Okay? Let's look at this. Let's write the DTFT and the DFT of the finite sequence. Okay? A finite sequence. Finite sequence of length n. Okay? The nth point DFT, nth point DFT of x of n is the following. Pay attention here. This is exciting and important beyond that. I'm just writing the sum, okay? And now I'm just going to express explicitly what is w sub n to the power of kn. It's really e minus j 2 pi over n, capital N times nk, okay? I just expressed that. Now, let me write the DTFT of x of n. The DTFT is a sum from minus infinity to infinity of x of n e minus j over g minus j omega. Okay? It is an infinite sum. However, my sequence is finite. Hence, my sum only goes from 0 to n minus 1. Stare at this long enough. You staring? Yes? What is the difference? The difference is that here I have 2 pi over capital N times k, and the rest, like if I replace these with omega, it will be exactly the same. Okay? So if omega would be equal to 2 pi over n times k, those would be exactly the same. What does that mean? What does that mean? I mean, I could have just picked those numbers. Let me pick a particular k, and then I know what the n is. I know what 2 pi is. 6.28. I know what 2 pi is. I can put it here and evaluate that function, the DTFT, at a particular frequency, correspond to that k. And then I can pick another k and evaluate. Basically, it's evaluating the DTFT at particular frequencies. It is sampling the DTFT. Okay, that's what it does. That's great. Okay, so the DTFT are samples of the DFTs are samples of the DTFT at n equally spaced frequencies. Awesome. I don't need to compute and then sample. I can directly sample this, and later we'll learn there's a fast algorithm to do it quickly. That's great. So X capital, like the DFT of at point K is really equal to the DTFT evaluated omega equals K times 2 pi over n. Yep.
Are there any functions for which the DFT would result in a loss of information in a DFT?
Pardon?
Are there any functions for which the DFT would result in a loss of information when you take the transform and the inverse, and the DTFT would not?
So the question was, is there a place where the DTFT would result in a loss of information, DFT would loss of information, the DTFT would not have all the information in. So as long as your sequence is finite with length n, and you compute the DFT with at least size n, there's no loss of information. Okay? Because all the information is actually there. Interesting, right? It is an orthogonal transformation, so information is preserved, yes?
What if you do a DFT with more than n points, but then you throw away some and do the I DFT of that? You get the second one.
You throw a what?
Sample.
Oh, in the DFT? Well, okay. Well, it depends. If you do more points and then throw away, depends how much you do.
What if you do 2n and then you throw half of it?
Well, you tell me that. What do you think? It could be. Because if you think about this, effectively you'll be downsampling. Actually, let me give this you this. Next one will show you this example. Basically, give you the answer. So let's go back to the moving average example, where we sum over E minus J omega n from n equals 0 to 4. Okay? So if you recall, the DTFT had this expression, which is a nice periodic sink that's modulated periodic sink. 2 prefixes. Okay? Modulated periodic sink. Okay? So if you look at the 5-point DFT of that, 5-point DFT of this, that's really like a DFT of a constant signal. So if I look at the 5-point DFT, it evaluates here, and then evaluates that periodic sink at this point, which turns out to be the zero crossing. And this one, and this one, and this one, and that's it. So that's why it looked like a Dirac, like a discrete Dirac, because we evaluated the DTFT at the zero crossing except here. Okay? But if I do a 10-point DFT, I'm also evaluating in the middle. Hence, I got a sampled periodic sink. Okay? So 10-point DFT, I do that. So then back to your question, if I compute a 10-point DFT of a 5-length sequence, and then I go and throw away half of them, yes, I still preserve that information.
And it doesn't depend which 5.
Actually, probably it does. Because if I throw these 5, right? So it does actually depend on that. Okay. By the way, this art is by Murat Archak. Okay. I took some of his slides previously, but he just has this amazing handwriting. It's just beautiful. I had to preserve some of that. Okay, but the thing is, this is a little bit awkward representation. So k equals 0 is really DC. Then it increases to samples to get to omega equals pi, but then like you go the other way. So it's kind of like shifted, right? When you compute the DFT, it's really, you get like half of the first period of the DTFT and then half of the second period of the DTFT. Okay? So k equals 0 is omega equals 0 frequency. And so in order to make it look like a DTFT, by computing the DFT, you can use what's called FFT shift to shift the spectrum such that omega 0 is actually in the middle. Okay? So, ready? Thank you. That's my contribution here. Okay, so now when you do FFT shift, you basically take the 1/2 and then shift it that way. That's what FFT shift does. And that's in order to just look at that spectrum so it makes sense that the DC is in the middle and positive and negative frequencies are on both sides. Okay? Questions? Who has not seen all that before? Why am I teaching this? This is all a review, by the way, because have you ever seen the FFT before? Like how to do that? Who has not seen the FFT before? Like how to do it? Oh, wow. Who has not seen the short-time Fourier transform? Who has not seen wavelets? Like in class? Okay. Okay. All right. So we're getting there. We're building language. Okay? Okay, so what about the relationship between the DFT and the inverse DFT? Turns out that they're both are computed very similarly. Your kernel is minus, like this omega w sub n to the power of kn, either a minus or a plus, right? So it's kind of similar. So let's a little bit play with algebra here. And let's say, what is n times x conjugate n? Okay. If you write this down, you can write this as n times something, and we want to compute x conjugate of n. What is x? What is x? I can write x as the inverse DFT of capital X of k, right? So x is also the inverse DFT of capital XK, small x. Okay, so this is the inverse DFT. That corresponds to x. And then I take a conjugate, right? So if this is x conjugate, then it's exactly the same thing. N times x conjugate, this is x, and I take a conjugate. Okay, so let's take this star and move it in. What is the star? You take conjugates of the, and I have n times n here, so those cancel. So now I have inside x conjugate of k, and then a plus here instead of a minus. But wait a second. Wait a second. What is this? This is also the DFT of this function, because now it's plus. Right? That's the definition of the DFT. If I change variables and instead of k, call it n, it will be the DFT of this function, or this vector, or sequence. Okay? So it is the DFT, the Fourier DFT, of x conjugate of k. All right? Because that's the DFT of this. So DFT of that. Great. But as it turns out, n times x conjugate is also n times, what is this? The inverse DFT of x of k, and then complete conjugate of that. So now you have a relationship between the DFT and its inverse, that they could be similar through some manipulation. So the DFT of x conjugate of k is the same as n times the inverse DFT of xk, and then take all of that and compute conjugate. Or you can write it that following way with 1 over and so on and so forth. And the question is like, why it's even useful? Why is it even useful? Same type of computation, so? Right. Does it help? Let's say you have fast algorithms for the forward Fourier transform. And I wrote a function. FFT. Now I want to compute IFFT fast. Well, who knows how to program? Kind of. What if you already written code? Are you going to be reusing it? Absolutely. So if I want to write an inverse FFT or inverse IDFT, what I could do is take my sequence, compute the complex conjugate. I'm going to take the DFT, multiply by 1 over n, take the complex conjugate. That will give me the IDFT using the DFT. Okay? So I have a sequence that I want to compute. Like I want to compute the IDFT of x of k. I take its conjugate. I compute the Fourier DFT. I take another conjugate and divide by n. Okay? So wrap in that function, right? I call another function. I just do some scalars operations, things like that, and that's it. Okay? Cool, right? And actually taking a conjugate operation is even simpler. You don't need to multiply by anything. You just need to make the imaginary part negative. Okay, it's changing often just the sign. Okay, so simple. Now, once you have finite sequences, you can represent them as matrices. And I love matrices. Matrices are great. They're square or rectangular, either wide or thick or perfect, and you put numbers in them in orderly way. And it's a great way to describe things. Okay? So here's the DFT. I want to compute the DFT of the sequence x0 all the way to xn minus 1. Well, I just fill in the values in that sum as entries in that matrix. And those entries would be, for capital X of 0 in the frequency domain, will just be varying, having a k equals 0 and then varying n. Turns out, doesn't matter here. This is all just ones. Hence, you just sum these to get x of 0. Kind of makes sense. This is DC. Gives you the sum. And then for any other value, like some other arbitrary x of k, then you put the kernel here, which is w sub n to the power of k times 0, then 1, and then k times 1, k times 2, k times n, and then k times n minus 1. Right? And then you get x of k. Okay, and so on and so forth. So you can represent the exact sums by matrix vector multiplication. And it's going to be square if it's going to be an endpoint DFT. And it's going to be long if it's going to be a larger point DFT. Okay? Does this make sense? And it's going to go to infinity if I want to compute the DTFT some way. It's going to be infinite. Because I'm sampling really fast. The IDFT, very similar way, except that I also need to divide by 1 over n. Now, the sad thing about that, when I stare at this, you kind of want to cry. You want to cry because this matrix is full. It's not sparse. Computation, matrix vector multiplication of a dense matrix is of the order of n squared, which everyone doing numerical linear algebra would immediately start getting, irritated eyes and kind of water starts falling off. And you go like, oh boy, right? But then, like epiphany appears, and then you stare this long enough, and you see, well, there's also a lot of structure there. All these W's, sub n's, I mean, they have like, maybe there's redundancy. Maybe there's structure. Maybe I can do something about that, okay, in order to reduce computation. That's what we're going to talk about afterwards, okay? But there is. So stop crying. Okay, so you can write the DFT as a matrix operator. So we can write it that it's that capital X is just omega sub n. This is the matrix multiplied by x. And then the inverse one is going to be 1 over n, this W conjugate, the DFT matrix conjugate times x. Yep. And so you can kind of play with stuff. For example, what is x? Is the inverse DFT of capital X. Well, that's great. But what is capital X? Well, it's the Fourier DFT of x. So I've got 1 over n, that times that times that. So I know that x should be equal to x. Hence, that stuff over here should look like the identity. Right? As it turns out, it is. Because this multiplying this by that will give you the identity times n. And why is that? Because it's orthogonal. Okay? So these are orthogonal vectors that sum to n. So it has a sum to n. And so you get that back, as expected. Okay? Question? Yeah. That's DFT n, right? DFT n. Yeah. So you do DFT n and then IDFT n, and whatever n is, even if your sequence is smaller, you can still do like n. Right? So yeah, it is square. Properties of the DFS. So all the properties are inherent from the DFT inherent from DFS because they're the same thing. So you cover them. I'm not going to prove anything, but I'm going to just mention them. It is linear. What is linear? You can represent a matrix vector multiplication. Of course it's going to be linear because this is linear algebra. Okay? So it is linear. Okay? You can write those DFTs as well as just matrix vector multiplication. Then anything then comes out of that because this is a linear operator. Circular time shift. So now, when we talk about time shift, because we're going to talk about sequences, I mean, just time shift is going to have some implication, but a circular time shift will correspond to a modulation by W sub nk. And that's where things become tricky. We're going to talk about circular things, circular shifts. Okay? So, if you have a sequence that is periodic, looks like this, what is a circular shift? Circular shift is as if you shifted that signal but kept the same window. Okay? If you do that and you compute the DFT, you'll get a modulation. If you just shifted that, different things happen. Okay? You don't necessarily just get the modulation. Okay? All right. If you shift in frequency circularly, you also get a modulation in the signal domain, in the sequence domain. If you conjugate one, you're going to get a flipped conjugate of the other. Okay? So conjugation in one domain is a flipped conjugation. If you have conjugate symmetry if you have a real signal, then you've got a conjugate symmetry, again, using a flipped version, but it's flipped with a period of n. What does it even mean? So let me give you kind of a tip, because this could be really confusing. Let's say you have a 4-point DFT. 4-point DFT. Pay attention. This is important. 4-point DFT. That's a sequence, right? Look at the colors. Red, orange, yellow, green, blue. Right? Purple. Red, orange, yellow, green, blue, purple. Okay? So that's the colors of the rainbow. Red, orange, yellow, green, blue, purple. That's the song. What's the what are come on. I mean, it's like 5-year-old indigo. I mean, like, come on. All right, doesn't matter. Okay. 4-point DFT. what is the symmetry here? I know that the sequence is real. There has to be some symmetry here. So here's how you kind of, it's kind of confusing. I don't remember. This is even, this is odd. I don't know. Okay, so what you do is you just create kind of a periodic one. That kind of makes sense what the symmetry is. Symmetry, conjugate symmetry between these two. Okay, so 1 and 3 should be conjugate symmetric. And then also 2 and 2 should be conjugate symmetric. But wait a second. What does it mean that the same number is conjugate symmetric? It is real. That's right. What if the sequence is odd? You're going to have a different symmetry. Again, you do that. 1 and 4 has symmetry, and then 2 and 3 has symmetry. Okay? So now there is no real extra one. Okay? By the way, this one is still conjugate with itself. Hence, it is real. Okay? So, conjugate symmetry, these two are real. Conjugate symmetric, this is real, and these are conjugate symmetric, right? So you got to remember that. Parseval theorem can be easily proved by going through matrix notation. Okay, if you just write it in matrix notation, so this is really the magnitude of this conjugate that is the magnitude is exactly the sum of that, and then you can show that it becomes exactly the same this. Okay, so maybe we'll make it in the homework. Circular convolution. That's the thing we're going to talk about next time, so I'm not going to spend too much. But circular convolution is assuming, as you slide them around, that they kind of wrap around each other. So think of it as like having a circle, and you're kind of like rotating one against the other, multiply and add, multiply and add, multiply and add. And one thing I have to say, and I'm going to cover it next time, but using DFT, circular convolution becomes easy. Linear convolutions are useful, not circular ones. So next time we're going to show how linear convolution and circular convolution correspond to each other, and then use DFT to do linear convolution. So we're going to talk about that on Monday. So you have the whole weekend just to think about what you missed this week. And have a nice weekend. You decide if you want to put it on the homework. You decide if you want to put it on the homework.
It's probably in the book.
It's not just only in the book, it's in the slides too. I'm going to go over it again. Oh, the battery.